Recording. Hello, welcome to Organic Chemistry 2341, our Monday, Wednesday class here at 12:30 noon. Good afternoon, everybody. I hope you're doing well and getting those COVID tests on a regular basis and hopefully coming back negative. Okay, so I wanted to remind everybody that we're going to be continuing with Module 3 and 4 this week. We're going to also finish up Module 4 next week and have a little bit of a review for our first exam, which is on February 17th, okay, Wednesday, February 17th. You must have your Top Hat up and running for that because it will be given on Top Hat, okay? So for that day, you'll just go ahead and log on to Top Hat, get everything in. You'll need an ID, a couple pieces of blank paper, and just all the regular stuff. It'll ask you to scan your room. It will ask you for your ID. It can be any picture ID, by the way, your Texas State ID and stuff like that. In Proctorio, it's completely recorded on video and stored on a server. I don't even look at the videos unless there is a high level of suspicion. Usually it's a dog barking in the background, so I can usually let you back in and stuff like that. If you have any problems at the beginning of the exam, which will start at 12:30, go ahead and email me. I will be monitoring it live. I will sit here and make sure everybody gets in and starts the exam as soon as possible. The format will be multiple choice questions. I believe there are 30 multiple choice questions from chapters 1 through 4. Look to the homework for the style of question and look to what we talked about in class for the content of the questions. Okay, so that's the general thing I want you to see on that. And I also have a review highlights of chapters, what I call hot topics for chapters 1 through 4. That can be found on campus under files. Okay, so might want to take a ping at that and look in that, and maybe start studying chapters 1 and 2. Make sure you have what you need to do that. Okay, any questions about our upcoming exam or our class today? Okay, go ahead and ping it in the chat or just interrupt me, that's fine. I'm gonna go ahead and start sharing my screen and start finishing up our chapter 3. Okay, so let's see if everything goes where I want it to. Yes, all right. So when we last spoke, we were talking about the different aspects that can change the acidity from one thing or another. And we talked about electronegativity and size, and that's how far we got on that. And so the idea what we have for this is that the electronegativity, if we're going across the row of a similar sized material, the acidity is always going to be with the one with the highest nucleophilicity, okay? The one that wants those electrons more is going to be willing to take on a negative charge. If you're willing to take on a negative charge, that makes that hydrogen more acidic, okay? But then we also found there was a competition there that if we had a large ion that could also distribute a negative charge very well, that the size won out on that. So when we go down a column, the bigger the size ion produced, the more stable it is, and therefore the more acidic it is, okay? So when given a choice of down a row, look for the most nucleophilic. Given down a column, look for the largest ion. Okay, questions on that? Okay, so I mean, and I'll show you some pKa values here in a minute to strengthen that here. Okay, so this is going to go ahead and compare the sizes and the nucleophilicities with their pKa's. So notice here when we go from fluorine to oxygen to nitrogen to carbon, they're all about the same size, and the nucleophilicity is increasing here, and therefore the pKa is increasing. Decreasing. They are becoming more acidic. Okay, so our HF is 3.2 pKa. Our water is 15.1. Also notice that HF is not a strong acid. It is not 0 or below. It is a weak acid in our system, okay? And the pKa of the ammonia is 36, and the pKa of the hydrogen on that methyl group is also very high at 50. So basically that is the least acidic compound on our row, and it follows with nucleophilicity. Now let's go down in size. We said that going down the row, down a column here, it goes by size, right? So in down a column here, we have fluorine, which is the smallest ion. It's that 3.2. Then we go up to -7, -8, and even -10 for HI, making HI, or hydroiodic acid, the most acidic acid we're going to be dealing with in this class, okay? But it's not just the halogens. Notice here, when we go down this row here, these all have 6 valence electrons, and we go from oxygen to sulfur. We've increased the size because we now have a 3 energy shell, a primary energy cell of 3, and that makes the molecule the atom bigger, and our pKa drops in half. And then selenium, which is down there, it almost drops in half again. And by the time we get to tellurium, it even drops again. And that drop has everything to do with the size of the atom, okay? But notice as we go in this direction here, notice that it's a nucleophilicity. So the more electrophilic atom is going to be the stronger acid. Okay, so do we understand that concept and how to use the down columns and across? Across is determined by electronegativity, down is determined by size. I had that question in the chat, and that is correct. Okay, so, and that works for, you know, all of the pKa values for all of the, quote, acids we're talking about. Now, I said, quote, acids because right here, that hydrogen can be pulled off by a very strong base, but I would not call that an acid by our traditional definition. That's why we have to go with that Bronsted-Lowry acid-base theory and that Lewis acid-base theory. Okay, so we had electronegativity. Well, how can we also influence electronegativity but not actually have it with that actual atom, but through bonds? If we have an effect of electronegativity, but it's not the atom you're directly attached to, on the exam, you'll always have a periodic table at the beginning and the end. And if you remember the trends, you should be able to figure it out. There's a question in there about, will we be given a table like that in a question? You'll always be given a copy of the ACS approved table of contents. I'm sorry, periodic table of elements. And you should be able to have those general trends understood so that you'll know that nucleophilicity goes up and over and size goes down, and you know some of the different general trends we'll talk about. You just need to have those memorized, okay, or understand. Okay, so if we're not talking about the atom it's directly bonded to, but we're talking about atoms that are adjacent to it, we call that the inductive effect, because what's going to happen is that electron negative atom, while not bonded directly to your hydrogen, can pull electron density through the sigma bond. And when it pulls the electron density through that sigma bond, it changes the net charge on the atom it's actually bonded to. So we start with the nucleophilicity it has, and then if we have a more electron withdrawing atom, it's going to draw it away from that. So what does this look like? Okay, so what it looks like is if we start with something like these compounds here, and this is just your nice simple carboxylic acid. We have carbon, hydrogen, and oxygen bonds. And so this is what we would consider our baseline. All we have are carbons and hydrogens. Those are fairly nonpolar bonds, and those have very similar electronegativities, okay? If we put a chlorine at the end of the chain here, that chlorine is very electronegative. If it was directly attached to the hydrogen, it would be a strong acid, okay? But it's not. And so what it's gonna do is it's gonna pull electron density from that carbon. This one's going to pull some, this one's going to pull some, and this one's going to pull some, making this anion more stable, therefore making it more acidic, okay? Notice the acidity, the pKa decreases, which means the acidity increased, okay? So, I mean, that's pretty far away, and that's a very minor, difference in acidity. What if we move that over one bond? And so we only have to pull it through 3 bonds before we can start affecting the charge on these oxygens here. The pKa goes down, the acidity goes up again, okay? So the point of the inductive effect is that you're pulling electron density through a sigma bond to make the material more acidic and more likely for the hydrogen to leave. Now, let's go ahead and get really close to it. So we only have to pull through 2 bonds right here. If we pull through 2 bonds like that, it drops again. Notice the effect is greater now. It only has to pull electron density through that 1 carbon-carbon bond, therefore intensifying the effect. Here it's 3 carbon-carbon bonds. Here it's 2 carbon-carbon bonds. Here it's 1 carbon-carbon bond. And notice the effect is increased and amplified with the fewer number of double bonds you see, okay? All right, so do we understand that that nucleophilicity effect can be directly in the previous question, in the previous demonstration, but it also can be indirectly or through an inductive effect, through bond effect in these acids as well, okay? Okay, so that being said, that inductive effect is determined by the nucleophilicity of the material and not by the size of the ion. Here it's direct nucleophilicity attack. So what we can see here is if we have iodine, bromine, chlorine, and fluorine all in the same position on that carboxylic acid, we see it follows the exact correct nucleophilic trend. Fluorine is more nucleophilic, therefore it has the most acidic system at the 2.5. Then next most nucleophilic, making iodine having less of an effect on the acidity than the fluorine does. And it's directly correlated to that nucleophilicity. We don't care about size anymore. It's all about how many electrons they can pull through that bond. That's why the trend actually follows with the nucleophilicity in this case. Okay. But if you don't just want to add a different halogen, what if you add more of them? Turns out the effect is additive. If we start with just hydrogens on our system, this is our baseline acetic acid, a good pKa to remember. By just putting 1 chlorine on there, we see a dramatic effect by just that nucleophilic atom pulling away some there. But if we add another one, it drops again. And if we add 1 more of them, it actually drops to almost a strong acid right here. It's a 0.7. And if you had 3 fluorines here, I think it actually does drop it to a strong acid and being in the negative number. So not only does the atom affect the acidity shown above here, but the number of them pulling away can also increase acidity. The higher the number pulling, the more acidic the compound will be. Okay, so does that make sense that if we're pulling electron density away, it stabilizes that conjugate base anion, and therefore the hydrogen is easier to lose? Okay, that's what we're talking about in these, how we're making it easier to pull that hydrogen off. Okay. All right, questions on this slide? Do you have to memorize the pKa for each of them? No, there was that list of 20 or so that are in the lab. Okay, I'm sorry, there was 20 or so that I listed on a previous slide. I circled, I said these are the 10 or so you might want to look at and memorize, because those are the ones like water and alcohol, the alkyne, the alkene, the alkane, acetic acid. Those are the ones that you need to have a good idea where they are, where they fall. Yes. Sorry, I don't know why people are texting me right now. Hang on. Okay, I'm gonna have to do that in a minute. All right, so are halogens the only things that can be electrophilic or nucleophilic? No, that's not true. Anything that can actually have a formal positive charge bonded directly to a carbon can act as an inductive electronic drawing group. For example, when we drew the section here, I could, when we calculate out the formal charge of this nitro group, we see that the oxygen has a negative charge, but the nitrogen here has a positive charge. Okay, what that means is that positive charge itself acts as an electronic drawing group, and we can draw the electron density away from that system. And all right, hang on, I need to pause for just a second. Somebody's having trouble in one of the teaching labs, okay? Talk amongst yourselves, please. Ooh, ah.
So y'all feeling prepared for that test next week?
No. Not one bit. No.
Getting there. Is this y'all's first time or second time taking this class?
First.
All right. Sorry about that. I am back. The labs were going crazy. I had to answer that one. Sorry. Okay, so halogens are not the only electronic drawing groups we have. We also have anything with a formal positive charge on it can act as an electronic drawing group. Even though it's not, quote, very electronegative, the fact that it has that positive charge in there pulls electron density to help stabilize it. That means the nitro group actually is a very good group at pulling electron density away. Okay, and so let's look at that effect here. So if we just have carbons and hydrogens, the pK of our alcohol is about 15.9. That's one of those ones you might remember. Ooh, okay, all right, cool. And for the having a fluorine attached here, we can actually increase the acidity of this hydrogen of this alcohol by that inductive effect, and it drops to about 14.4 pKa, which makes it more acidic. So the fluorine inductive effect, that most electronegative element effect, only dropped it about 1.5 pKa points, okay? However, the nitro group, because it's a full positive charge, actually pulls more electron density away. And notice our pKa drops a whole 5.4 pKa values, making it much more acidic than the inductive effect allowed by just a single fluorine. So anytime you can draw a compound with a formal negative charge in its Lewis dot structure, it will act as a strong electron withdrawing group. In fact, I believe nitro is one of the strongest electron withdrawing groups we have and will be using throughout the semester. Okay, questions on electronic drawing groups and the inductive effect? Okay, so there's also a solvent effect, okay? Because when you pull off that proton, you have two ions now, right? The proton's gonna have to be on some Lewis base, and that creates a positively charged species that has to be supported by the solvent. And then the deprotonated material is gonna have an anion, that's your Lewis base or your conjugate base, and it also has to be supported. So things that help disperse charge, like water or polar solvents, are the better solvents for this particular material. Okay, if your conjugate base is not very soluble in water, that's going to decrease its acidity. It's going to increase its pKa because it can't give that away and stay a stable ion. That's, remember, all about acidity is about how stable the ion formed is, the iodine ion, the acetate ion. If you make it so it's unstable because of solvent, it also changes the acidity. So let's look at that with respect to acetic acid again. This is our acetic acid, 4.75, 4.76 here. If we take off this methyl group here, it actually becomes more acidic. Part of that is because we can hydrogen bond a little bit more. Part of it is that the hydrogen here has just a little lower electronegativity than the carbon does. And so we actually see a slight increase in carboxylic, in the pKa. However, if we start putting methyl groups on here such that this becomes less and less water soluble because it has this van der Waals bonding section on it. So remember, these are only do van der Waals bonding, they don't do hydrogen bonding. So you're forcing the water away from the charge being formed. And so what we see is a decrease in acidity, increase in pKa. And even when we get to this trimethyl version of acetic acid here, it goes up again, meaning it's even less acidic. So let me describe that graphically, what's happening here. So in the most acidic one here, we have the formic acid. So it's not acetic acid, doesn't have that methyl group there, but it's formic acid. And notice that the water is by itself, just hydrogen bonding to itself here. And that's what it's kind of doing there. And then once you separate your charge, you end up with your hydronium ion here and your formate ion here. And notice that there's a lot of places for these the water to hydrogen bond to the two ions formed, okay? So it's very well supported, therefore it is very acidic. It helps the acidity of just the acetic acid, okay? In contrast, once we put this big van der Waals only group right here, our hydrogen bonding can't support any ions coming from this direction. And so if you look at this whole area here, there's no support from any of the hydrogen bonding solvents. And now once you get your hydronium ion, which is down here, and your carboxylate ion here, you only have very few interactions with the water being able to support that large trimethyl acetate ion. Okay. So the fact that you cannot hydrogen bond close to it decreases its acidity because that makes the anion formed less stable. Okay. So, so I think that is a dramatic indication. And notice that less stable is in the first one we did and the second one we did and the third one we did. It's all about making the more stable conjugate base. The happier the conjugate base is, the easier it is to get that proton to leave. Okay, there we go. Ooh, not that. Poodles. Oh, we're almost there. Hey. Okay, so that's where we were. And so the next thing that would make that anion even more stable to being happy and stable is the fact that we could delocalize the charge over one or more atoms. So remember when you're doing Lewis-Dot structures, when you draw acetate ion, and we drew the two Lewis-Dot structures saying, well, the oxygen could have the negative charge on this one, or the other oxygen could have the negative charge on this one. So they were contributing resonance contributors. That we're going to use that same premise to spread that charge out, making that more acidic. So I'm going to use the example with oxygen. So we're not changing electronegativity or size. And if we have the oxygen on methanol here, and we deprotonate it here, the entire negative charge stays on that oxygen, right? So that entire negative charge stays on that oxygen. And just because of electronegativity here, we have a pKa of 15.5, okay, right around water. Okay. However, when we change it to the carboxylic acid here, if we look at the two competing resonance structures here, we have the negative charge on this oxygen, the negative charge on this oxygen, which means we're actually spreading that negative charge out over both of these carbons, both of these oxygen, making it about half, sorry, it's not the right symbol, making about a -1/2 charge here and a -1/2 charge here. that makes it more stable. You've spread that charge out over more space. Just like spreading it out over iodine being huge, we've actually spread it out over more carbons in this case, and therefore it becomes more acidic, as indicated by the drop in the pKa to 4.74. Funny, that's the third value for acetic acid I've seen in this slide deck alone. Okay. But they're all 4.7, 4.4, 4.5, 4.7 something. Yeah. All right. So do we see how delocalization can help with making those stable systems as well? Okay. But it doesn't just have to be over two atoms. It can be over another system. So in the case of phenol here, and when this is an alcohol on a benzene ring, it's called phenol. And because of this alternating single and double bonds, that gives us an opportunity to push electrons around that ring and move them around quite a bit. So if we were to deprotonate the alcohol portion here, this negative charge could then move around the ring. And so we'll have a little bit of negative charge here, a little bit of negative charge here, a little bit of negative charge here, and a little bit here, increasing the number of atoms our negative charge is bound on. So I think it is, okay, and that way we have it over 4 atoms, and it actually drops the pKa. It makes this much more acidic than all the other alcohols because of that. In the previous case with methanol, that oxygen couldn't move that charge anywhere else. But phenols, because of that conjugation with the ring here and the ability to delocalize that charge, it is the most acidic of the alcohols. However, not as acidic as the carboxylic acid. All right, I have a question in the thing. Is more stable, more basic, less stable, more basic? Okay, the more stable the the conjugate base, the more stable the conjugate base, the more acidic the acid. Remember, a conjugate base is going to be the opposite of whatever the acid was. So if the acid was strong, the conjugate base is very, very weak base, and that makes it stable. If the conjugate acid was very weak, it makes a very, very strong base, makes it very reactive. Okay? All right, so that's a good question. So we've changed it by looking at the electronegativity and the size of the element. We've changed it by pulling electron density through carbon-carbon bonds. We have changed the system by being able to delocalize that charge over a greater number of atoms. Every single time, we're making it easier and easier for that hydrogen to leave if we can do these things of having the bigger conjugate base, the more stable conjugate base, or stabilized over a greater number of atoms conjugate base. Okay, so the next thing we're going to talk about is the hybridization of the atom that is the hydrogen is bound to. Okay, so the first thing we want to do with that is we want to look at really the carbons. It's most dramatic in the carbons. And if we look at the hybridization of the carbon, it actually changes the acidity of the hydrogen on those hydrocarbons. Okay, so we're just looking at that carbon-hydrogen bond and trying to modify the acidity based on hybridization. So in the case of an alkane here, so we have Sp3 hybridized thing, we actually have, remember, in our Sp3, we've taken 1 s orbital and 3 p orbitals and turned them into 4 equivalent orbitals, okay? So that means that there's about 1/4 of each of those orbitals has s character, okay? And it turns out s character is closer to the atom and stabilizes charge more, okay? So if we had more s in there, it would help stabilize that negative charge. So let's just start there. Now, if we move up to our Sp2, we've taken our s and 2 p's and spread it out over 3 orbitals. So we're 1/3 of that s orbital is spread out over 3 different equal orbitals, giving it 1/3 s character. So if we have more s character and that's held closer to the atom, that should be more stable anion, right? So let's go to Sp right here. So in Sp hybridization, we've taken an s and a p and spread them out over 2 orbitals. making it 50% S in one orbital and 50% S in the other orbital, right? So that's the one that's closer bound, and therefore it's more S character, so it should stabilize the charge even more, okay? So let's see if that's true. Let's look at our pKa's. Our pKa of our methane, or our hydrocarbons here, is 70, okay? That's a very high number. All the hydrocarbons are going to be in the 50 to 70 range. They're very high. They are the weakest acids we're going to deal with, okay? But the alkenes right here, they are not as high. They're in the 44 to 45 range, okay? It has everything to do with we have more S character. More of that electron density is held closer to the nucleus, therefore it can stabilize that charge better, okay? Now, when we're half S and half P, it even drops again to 26, the most acidic hydrocarbon hydrogen we have. Okay, so that is why we see that trend in, even though they're all carbon and they all have the same electronegativity, it's the amount of S character that is used by each of those hybridized bonds that allows us to change the acidity of different carbon hydrogen atoms. Does that make sense? Let's see. Don't have to let me in. Okay, great. All right. So this also is true with the other atoms, you know, because of all those group 2, that row 2 elements, they all do Sp3 hybridization, they all do Sp2 hybridization, and they all can't, well, the nitrogen and carbon can do Sp hybridization. But it's all about also the size of the orbital formed. So if we look at that and we add to the system our nitrogen compound, so now we have a nitrogen-hydrogen bond, and nitrogen is a little more nucleophilic, a little more electrophilic than carbon, but it also has Sp3 hybridized bonds. And its Sp3 hybridized bond is actually smaller in size because of its electron affinity, and it allows it to be intermediate between an Sp2 hybridized carbon and the Sp hybridized carbon. And so should fit in between them on the pKa scale. And that's what we see. We actually see that our Sp3, which has the largest orbital here, the most P character, then we move down with the ethylene, has less P character, more S character. This actually has, because of its wanting to pull the electrons tighter to the center because of its electron affinity, it has a smaller orbital and therefore has that intermediate there. So the hybridization works also within the different elements. And we'll see that as we change the hybridization on nitrogen here, we should see that continue to get more and more acidic as we go from a nitrogen with an Sp3 to a nitrogen with an Sp2 to a nitrogen with an Sp. All right. So does that kind of sit well with everybody? That's kind of something that you can get a grasp on. Okay. So now let's talk about the concept of base strength. Okay. For the first half of this course, we're going to almost always use pKa's, but I like to introduce pKb's here because when we talk next semester about amines, we have to talk about base strength and the pKb's. Okay, so the first thing we need to know is that strong bases tend to be unstable and very reactive. Okay, they just want to suck up a proton from somewhere. They don't care where. They aren't going to be very picky. Okay, so which means that the weak bases are going to be more stable and less reactive. Okay, so that kind of, it sounds like the question that's in the chat room, but that's a different thing. We're talking about the weaker, the stronger the base, the conjugate base, the weaker the conjugate acid, the acid. This is different. We're just talking about the base strength of itself. Okay, so let's describe that. Let's take this and look at our first really strong base, this sodium amide. It's actually on our pKa chart there, as when we deprotonate our ammonia, with a pKa of 38, we actually make a very strong base right here. And it has a pKb of negative 22. Okay. And if we look at the acid strength on this side here, our water is 15.7. But when we dip this in water, when we put ammonia in water, what happens is the sodium amide picks up hydrogen, and now it has a pK of 36. So it's now a weaker acid than the acid we started with. And our hydroxide ion is only a negative 107. Okay. So that sodium amide is a stronger base than the hydroxide ion it forms when it gets dissolved in water. So that being said, when we compare the pKb's here, this is the weaker base and this is the stronger base. Therefore, our equilibrium is going to be shifted in this direction. Okay, so just like in the acid where the weaker acid wins out right here, when we talk about base strength, the equilibrium lies on where the weaker conjugate base is. Okay, so it's, just make sure you're thinking about the pKb as the base and the pKa as the acid, and the trends will follow. Okay. In contrast, when we have something like chloride ion here, chloride ion has a pKb of 21. Okay, so that's a high number, so that's not very basic, right? But its conjugate acid is very strong, -7. And water has an acidity of the 15.7, but the conjugate base is -1.7. So this is the stronger acid. So now we've moved to the stronger acid and the stronger base. So that means the chloride ion will not react with water to create HCl and hydroxide. Okay, the equilibrium lies in this direction. So our chloride ion is weak because of a high pKb, and it is fairly non-reactive. Our strong base here has a very high basicity because our pKb is negative, and therefore it's not stable and very reactive. Okay, does that so? Make sure we switch gears and we're looking at that negative. Okay. All right, questions on that? Okay, so now let's apply this to more organic compounds. Okay, and let's look at that table again. But the last time we only looked at the pKa side right here, thinking about how acidic things were. So now let's look at the other side, the pKb side. Okay. Now notice our values go up, down a little bit differently. In the pKb here, we start at -36, and we go all the way to +23 for bromine. Okay, so the range is a little different, but because pKa plus pKb or minus pKb plus pKa equals 14, notice there's only 14 difference between these. Okay, so you can always find exactly where it's going to be, and that's 14 between these as well. So you'll see that that's true for all of them. So when we make this anion here of that, it was a very bad acid, right? It had a very high pKa, but that's one of the strongest bases we have. Okay, so, and because it's a very strong base, it's going to be very reactive and very unstable. Okay, so we have to make it right away and use it right away. Okay, and that follows with the ethylene version plus the acetylene version. And here's that nitrogen anion we were talking about also. And then we have our alcohols. This is our T-butyl alcohol. This is our regular alcohol and hydroxide. And then we can go all the way down to that acetate ion is really, that's interesting. They should be, oh yeah, because you add them together. Yeah. You're going to get pretty close to that number there. That one's actually not 14. Interesting. Okay, and then water here is our differences in those. So the key here is that if you have a very negative pKb, it's a very strong base, and its conjugate acid is going to be a very weak acid. Okay. So let's look at that, how it affects specifically with nitrogens, okay? Nitrogens are what we consider our organic bases, and so knowing the trends of their pKbs will help understand which types of amines we're going to be using in our reactions as that Lewis base, okay? And it's also can be used as a Bronsted-Lowry base. Okay, so the idea here is that we have, number one, a lone pair on nitrogen. That lone pair on nitrogen, yeah, that's it, sorry. So the lone pair on nitrogen can reach out, act as a Lewis base, and abstract a hydrogen from something and create the conjugate acid here. So it's that lone pair that's reaching out and making that new sigma bond, and our nitrogen is then tetrahedral in structure after it forms that conjugate acid. Okay, now it does have a formal charge of +1, but it still can form it that way. Okay. Now, in general, all these amines tend to be fairly weak bases because we don't have an anion associated with it. We only have that lone pair reaching out to make that new sigma. Okay, so let's talk about amines and what influences them, their basicity. Just like in the case of acidity, resonance can affect the stability or the basicity of that lone pair on that nitrogen. Okay? So you got to remember when we think about our nitrogen here, we always have that lone pair on all of them, and that lone pair is most key to its basicity. Okay, so now if we just started with an amine on a benzene ring, we're looking at resonance so that we can actually put this lone pair in and out, and it can go around the ring just like it did with phenol. And therefore we can see that it has an ability to spread it out. What it does when it spreads out those electrons is it becomes a weaker base because those electrons do not have to stay on that nitrogen 100% of the time. They can be moved. For example, when we look at this one over here, there is no possibility for these electrons to be conjugated to anything. They are stuck on that nitrogen atom, and therefore they have a lower pKb, which makes them a stronger base. Okay. In contrast, if you have an electronic drawing group here, that electronic drawing group is pulling electron density away from the ring so that when we share our electrons over here, they're not shared as much because it's pulling that electron density away. I'm sorry, it's even easier to share those electrons in here because it's pulling some of the electron density away through an inductive effect, and our pKb goes up, making it a weaker base. Okay, and then if we have something that can act as an inductive withdrawer, but also we can put the negative charge here, we can add a negative charge here because of the electronegativity, and it can move over here. Our pKb is intermediate. Notice it doesn't change very much from the one without. So if you can move the lone pair from the nitrogen around the structure, your base strength is lowered. That is correct. Okay, and so that's the base strength as it applies to resonance. Okay, so let's look at the base strength as it applies to hybridization. Remember I said hybridization of carbon changed it. Hybridization of the nitrogen actually changes as well. In the case of acetonitrile right here, we actually have an sp hybridized nitrogen. And I said that should be the most basic of the system. And if we look at the conjugate acid of it, it is a very strong acid, okay? So I said that if with the sp hybridized, the acid of that would be very, very strong because it's getting stronger as we increase the amount of S in the hybridization. Our conjugate acid here is a negative number. It is a definite strong acid. But as a result, because our conjugate acid is a strong acid, that makes our base weaker. So that X character is not helping us in basicity. Okay. So let's look at Sp2 and Sp3 as it refers to nitrogen, and we'll see. So in the case of this compound here called pyridine, It's like benzene ring, but you take one of the carbons out and put a nitrogen in. And what that means is that your nitrogen here has to be sp2 hybridized because it has to have an unhybridized P to make that pi bond, okay? So that means the electrons that are in this, that are sticking out left over, must be in an sp2 hybridized. And if we look at the basicity of that, the basicity actually, the pKa drops, and therefore it's more basic than the sp. And if we look at the conjugate acid of it, it is not as strong as the sp. Okay, so it's following the same trend that we saw before. In the case of this compound here, this now has 3 bonds to it and a lone pair, which means it's sp3 hybridized, and it has an even lower pKb, making it a stronger base. And notice that the conjugate acid here is a weaker acid. Okay, so the trend in basicity with hybridization is the opposite. Sp is less than sp2, which is less than sp3. Okay, but notice that the trend in the conjugate acids here is consistent with what we heard. So the p orbitals are important for basicity, and the s orbitals are important for acidity. Not exactly. The p orbital, the s orbital, because it holds that charge more closely, holds those electrons more closely, makes it harder for them to share. So that more s character makes it harder for them to share because they're held in more tightly. So the s orbitals are still affecting basicity, but if they're held tightly, it helps the acid to be more s. It hurts the basicity because we're going the opposite direction. We're trying to share the electrons, not lose a proton, not have all the electrons to ourselves. So does that answer that question? That was a question in the chat there. Okay, so the trend is the same, but it hurts basicity because it's trying to hold those electrons even tighter with those more s's, making them less basic. Okay. All right, so, and then I said there's also an inductive effect. The inductive effect is directly related to, if it's electron drawing, what it's going to do is it's going to pull those lone pair electrons away, making them less likely to share with a proton. If they're less likely to share with a proton, it's less basic. Okay, and so if we go from that compound with the sp2 hybridized nitrogen here, and we look at the pKb, and by putting electron drawing group here, it becomes less basic. The pKb goes up. Okay, and if we put something that can actually donate a little bit of electron density to it, that means those electrons are easier to share. And if those electrons are easier to share, that makes it more basic. Okay, and that is corollary to the, I moved it. Hang on, I gotta stop sharing and reshare. If I move my screen too much, it doesn't like it. Here we go. There we go. All right, dismiss. All right. So do we see that the inductive effect, if it's an electron drawing, it's going to pull electron density away from that lone pair, making it less likely to share. If we have something that donates, it's going to make it more likely to share because there's more electron density on that nitrogen. Okay. So think of it, because acids and base are opposites. So what happens in acids is typically the opposite in bases. Okay. So because we're looking at it from a different perspective. Our bases want to share their electrons, but they have to have a lot of electron density to share easily. Our acids want to steal electrons from somewhere else, and by whatever they leave behind, the more stable that is, the easier it is to go to that new bond. All right, so there's also a solvent effect associated with this. Just like before, the anions and the cations formed during the process of making your acid-base pair relies on a solvent to support those charges. In this case, we're looking at water. And anytime your solvent is being pushed away by a hydrophobic group, it will decrease the basicity of the system. Okay, so by contrast, if we look at this one, just a dimethylamine in water, and it has a pKb of 3.27, which is a pretty strong base for an organic base. It's not below 0, but it's still pretty decent. By just adding another methyl group on that, making it a little more hydrophobic, the pKb goes up and the basicity goes down. Okay, and that has everything to do with just the added hydrophobic effect of adding that one methyl group. Okay. It's a very pronounced effect in solvents. Okay, all right. So one way to trick that is to, instead of having two alkyl groups that can flop around randomly in our system, we'll talk about that more in our module 4, but if we pulled them back and tied them so they actually took up less space, that actually can increase the basicity. Look here with these two big groups, imagine that these are flopping around here and taking up a lot of hydrophobic space in our solvent. By pinning them back and making them not so flexible, taking them away and having them take up less volume in your solvent, it actually increases the basicity. These electrons are more easily shared. Okay. So that solvent effect can be minimized by having a small circular amine, or a small heterocyclic amine. Okay. Now, we talked about free amines, but turns out that any nitrogen with lone pairs can act as a base. So we talked about pyridine and how it had a pKb, a pKb of about 3 here, and the pK there. And we talked about aniline and its pKb. But what can also happen is in the case of the acetamide, which is the amide with 2 hydrogens on it here, we can actually get resonance delocalization of that in around here, and it can act as a base. Even though it's right next to a carbonyl, and inductively it's trying to pull some of the electron density away, it can share that a little bit, and those lone pairs on that nitrogen make it a weak base. Okay, so we have 2 effects. We have the electron withdrawing of this carbonyl carbon, plus the idea that you can spread the electrons out over 2 atoms. That's putting less electron density on that nitrogen, making it a weaker base. Okay. So we can actually use acetamides and stuff as really weak bases in solution, and we can also use them as solvents as well. Okay, so let's go over the basics, the fundamentals of bases, okay? The atom, what atom is the charge on, okay? You wanna look at those, things as how do they compare in terms of electronegativity and size, okay? Resonance effects have an effect because you want to have those electrons on that nitrogen for sharing, or have electrons donated to that nitrogen for sharing. In the case of induction, which is our next thing. And then our hybridization changes as well. The hybridization actually is the reverse of what we saw for for acids, right? The more S character is not helping us in bases because it's holding those electrons more tightly because of the more S character. So that means the Sp3s are going to be more basic than the Sps. Okay. All right, questions on bases?
I have a question.
Yes.
It's not anything specific. I feel like I'm just getting a little bit lost in translation. Like I want to understand the big picture. Like what is the purpose? Why are we doing all this?
Big picture about acids and bases. It helps us determine which way the reaction is going to go. We always want to go from strongest acid to weakest acid in a reaction. Or in the case of bases, if we're using base, we want to go from the strongest base to the weakest base. So knowing those general trends and the effects of acidity and basicity help us say, oh, I'm going to put 2 chemicals I don't know together. What's going to happen? Now, in the following chapters, we're going to learn about nucleophilicity and using them as acids and bases, as Lewis acids and bases. And we're going to apply the Bronsted-Lowry stuff, which is the acidity, the pKa's, and where are the electrons and where is that new bond going to form. So we're going to add those two together in every single reaction mechanism as we go forward. Does that help? Okay.
Yeah.
Okay. All right. So I am going to continue on with chapter 4 to make sure we are on our, let's see, that one right there. And we're going to talk about acyclic alkanes, basically alkanes that aren't in cycles, and cyclohexanes. Okay. So up to now, we've learned a lot of nomenclature. We learned a lot of functional groups, and we learned a lot about the atoms and the nature of the bonds themselves. Now, with the acids and bases here, we're actually starting to see, ooh, there's a reason this bond's going to break and this bond's going to make. Okay. Okay. But now let's talk about the nature of that carbon-carbon bond and that nature of the hydrocarbons that we have. Okay. So we're going to go back and we're going to look at just those hybrid carbon chains and think about, first of all, that Sp3 hybridized bond to an Sp3 hybridized carbon and that sigma bond. Okay. So that sigma bond actually has the ability to rotate. Those two atoms can rotate around each other. There's nothing fixing them in space, okay? So that means that we can just have them rotate around. And they're, even though you can draw the same compound differently, so notice that the compound on the left and the compound on the right, they look like different compounds because that thing, but they're not. They're exactly the same compound, all the same bonds in all the same location, okay? The only thing that happened was we have that free rotation around a sigma bond giving us a different conformation, okay? So they're sometimes called conformers or rotamers because we've rotated a bond, okay? Okay, that doesn't mean that, you know, in our solution, we don't have something that looks like this nice structure here. We probably do, but it also means that because we have free rotation, I can rotate this bond around and make it look like that. And the probability of being some of it in solution is pretty high if there's not a high energy barrier to that rotation. Okay, so that means that we have a bunch of different conformations available to us. Not any one structure is, it's going to be 100% that in the liquid form. Okay. And so by looking at the conformational analysis or the energy it takes to switch from one form to the other, we can learn something about those, how the molecule is probably going to situate itself in solution at room temperature. Okay, so the first thing we got to do is remember what our line drawings are, and remember that we have our Sp3 hybridized. They're going to be tetrahedral. They're going to be 109.5 degrees apart, if at all possible. And every carbon on a stick drawing obviously is going to fill up all the vacancies with hydrogens wherever we have. Okay. So if we take just something in a stick line drawing, it would look like that. It would just be a line right here. I'm going to add the hydrogens so we can look at where those hydrogens are and where they go. Now, it's hard to do a one-dimensional to, or a two-dimensional line into 3 dimensions without having some special tools. So the special tools we're going to use for this is, we're going to have a, is this module on Canvas? It should be, and if it's not on Canvas, it is on Top Hat. I will make sure it gets uploaded to Canvas soon. Okay, let's see. So if we think about this red line, in fact, let me do this. These 4 atoms right here are in the plane of the paper. Okay, so we're trying to create 3-dimensionality. So we're going to take those 4 atoms. Oh, yeah, okay, cool. And put them all in the same plane. And so they're, imagine that being flat. Okay, now, how do we represent that we're having things come above the plane? Well, with that, we use this blue wedge right here. Well, technically it's a solid wedge. It can be black too. Solid wedge tells you those things, those hydrogens are coming out at you. And if we used a dashed line here, a dashed wedge, that means those are going behind the plane. Okay, so with that premise, on our taking a 2-dimensional thing and making it appear 3D so we understand what's happening. Now that we have that, what I want to do is I want to rotate this 45 degrees and look at it again, okay? And when we do that, we've lost that kind of place where our plane of the paper was. So we're just going to follow the colors of them. So when we had our blue wedge here, it turns into our blue hydrogen here. Our hydrogen was pointing back is now here, and the hydrogen in the plane of the paper is now here. But that carbon is now behind, starting to go behind it here, okay? So all we've done is rotated that 45 degrees. So now the next thing we want to do is rotate it another 45 degrees such that we're looking down these two carbons, okay? When we draw a diagram where we're looking down these two carbons, it's called a Newman projection. And the way we do that is the carbon in front has the hydrogens going all the way to the, has the bonds going all the way to the center. That represents this number one, this carbon right here. I'm just going to call it carbon A. So carbon A is that one there, okay? Now, the carbon that's behind here, I'm going to call carbon B, is represented by the round ring here. And notice those atoms are the ones that are bonded to it, okay? The ones that come to the center are bonded to the first carbon we see looking down the bond. The carbon with the round ring and those hydrogens are on the ring are the second atom we see as we're going down the bond, okay? Okay, so this is what we call a Newman projection. And the cool thing about it is, I mean, it looks like a little propeller spinning maybe, I don't know. So all we've done is convert our stick drawing into a three-dimensional stick drawing into a projection where we can look down there and see how these different things interact with each other. How are those different groups on adjacent carbons interacting? Okay, so, okay, we are at 1:30, okay, fine. All right. So we're gonna use that Newman projection to look at that rotation around the carbon-carbon bond right here. We're now gonna look at the rotating around this bond here and see what happens to these groups. How do they interact? So when we do that, when we take our sawhorse drawing and turn it into a Newman projection, we actually can see something now called a dihedral angle. So that's the angle between two atoms through space. Notice that it's not, these are not on the same carbon. This is on carbon B, this is on carbon A, right? So we're talking about two different substituents on two different carbons. And the angle that it forms between it in this particular configuration is a 60-degree configuration. Notice that's equally around all of them. That's 60 degrees all the way around, and all the hydrogens are spread out as much as possible, okay? We call this the staggered conformation because none of the atoms from carbon 1 are overlapping with the atoms on carbon 2, or A and B. That means that we have probably our lowest energy because we don't have any electron-electron repulsion from the different groups here. Okay. And so that gives us a starting point. Okay. Now, what if you were to rotate this around that bond? If we rotate from that staggered configuration we started with, this is the staggered configuration, we rotate 60 degrees such that the hydrogens are overlapping now. Our dihedral angle has now gone from 60 degrees to 0, and now we have a new form. This is called our eclipsed conformation on this side when we have that. So think about it, the hydrogens are going in front of one's in front of the other, eclipsing it. That gives us our eclipsed conformation. Okay, so now those hydrogens are now closer to each other than they were, and they each have an electron cloud on them. So they're going to start to push away from each other. So I think there's going to be an energy barrier going from that staggered configuration to making them eclipse and start to push away from each other. All right. So let's look at that again. So when we look at it from the side and we look at our 60-degree angle, if we turn over here, the amount that those hydrogens are interacting is very small. That's the smallest they can be in our system. And so we get a nice equilibrium about how far away those hydrogens are from each other. As we take that dihedral angle and go to 0, we now have those hydrogens are now closer to each other and they start pushing each other apart. Because of the electron clouds, they'll push each other apart. And that causes what we call torsional strain, okay? Because it's trying to torque these out of the straight from bonds from each other, and that gives us strain, okay? And each of these interactions between the hydrogen here is about 4 kilojoules per mole of energy that is causing strain, which means by adding all 3 sets up here, we have a total of 12 kilojoules of strain. Somebody have a question? Or the mic come on, okay. So if hydrogens cause a little bit of strain going through that, I wonder what bigger groups are gonna do. Okay, so let's actually just start going around the ring and doing 60 degrees, 60 degrees, 60 degrees, 60 degrees, and see what happens, okay? So when we start here, we have our relative potential energy is the lowest it can be, right? That's where our hydrogens are farthest apart. And by rotating it 60 degrees, we get to our first eclipse configuration. And we have a relative potential energy that's going to be 12 kilojoules per mole higher. Now, if it goes and continues to rotate that same direction, in this case, we're rotating counterclockwise. If we rotate it back to another 60 degree or staggered configuration, the energy drops again. And you can continue rotating counterclockwise and it'll go up again. And you can do that back and forth until you get that hydrogen back to where it was, okay? Now, because all the groups are the same size, we have this same increase in potential energy, decrease in potential energy, increase in potential energy, decrease in potential energy. Okay, so that's simple for ethane and just hydrogens. So let's extend that to butane, okay? The key with the butane is we have to figure out which carbon-carbon bond we're gonna look down because we have a total of 3 different carbon-carbon bonds we look down. But in this case, what we want to do is we actually want to look down this bond right here. And that's an eye showing that we're looking down that bond. The reason we want to look down this bond and between these 2 atoms is that we have one group on carbon A and one group on carbon B. Is there a question? Clearing the throat? Okay. Carbon A. We have one group on carbon A and one group on carbon B. And so we can look at the interaction between those 2 groups that are moving around. Okay. Okay, let's see. All right. So how would we draw that? Okay, well, by our Newman projection, to convert this into our Newman projection, we're going to have something where one of them is opposite the other. So we're going to start with our Newman projection in the front. And this is our carbon A. And we're going to put our CH3 on 1, 3, and then our hydrogen here and our hydrogen here. Then let's draw our carbon B, which has that ring there. And we're going to start with a hydrogen here, and a CH3 there. So see how I looked down this bond here. Right here, the first thing I saw was a methyl group and 2 hydrogens. Then the second thing I saw on the next carbon was this second carbon with 2 hydrogens and another methyl group here. So that gives us our new Newman projection. Okay, so let's do our conformational analysis of this right here. So I drew it in this configuration right here, where they're opposite each other. And that's considered what we call the staggered configuration, but it's also called the anti-configuration. The anti-configuration because the 2 methyl groups are opposite each other, okay? So one's gonna be up and one's gonna be down, so they're anti. It's not trans because we have free rotation. It's just an anti-configuration. So if we take that and rotate it 60 degrees, we end up getting to an eclipsed configuration. And notice we have a methyl and a hydrogen interacting, a methyl and a hydrogen interacting, and 2 hydrogens interacting. We already know that this one is a 4 kilojoule per mole interaction. So these must be higher to get that total of 16 kilojoule per mole higher potential energy. Okay. If we rotate at 16 more degrees, we get to a new configuration, something we didn't have in the hydrogens. And that's called the Gauche configuration. That's where our two groups are staggered but close together. Okay, so we can have a gauche on this side and on that side because our two large groups are staggered but close to each other. Okay. Then when we go rotate that 60 more degrees, we're now going to have an eclipsed right here. So our two methyl groups are interacting with each other. And then of course our two hydrogens here are adding 4 kilojoules per mole each. Okay, do we see how that's rotating around and how those different configurations go from our anti-staggered, our eclipsed, our gauche staggered, and our other eclipsed? Okay, now let's look at the energy diagram. Okay, when we look at the energy diagram, we see a slightly different picture than we saw before because we have those two new interactions. We have those gauche interactions that we didn't have before, and we're going to have this eclipse interaction where our two methyl groups are. So we're going to have a different peak. And if we look at that, we can see that we start at our lowest potential energy is where in our anti position. It's staggered. The two biggest groups are opposite each other, lowest potential energy. Okay. By moving into our first eclipsed right here, where we have a methyl hydrogen interaction, a methyl hydrogen interaction, and a hydrogen-hydrogen interaction, each of those methyl hydrogen interactions is 6 kilojoules per mole, and therefore it gives us a total of that 16. When we go into our, by rotating 60 more degrees and getting to our gauche configuration, so this would be a gauche with the thing on the left, and this is our gauche with it on the right, we don't get perfectly back down to the original system because our methyl groups are not opposite each other. They're still a little bit close in space, and that's that 3.8 kilojoule difference between the anti and the gauche. Now we go to the highest energy section there. It's the one where the two methyl groups are going to impinge upon each other. We're straining everything, and so that gives us a total interaction of 11 kilojoules per mole just for the methyl groups, giving us a total of 19. When we rotate 60 more degrees this way, we end up with our gauche again. And that's the same energy, whether it's on the left or the right, going up to an eclipsed and then finally getting back to our anti. Okay. So we understand why these diagrams are a little different than that one with just the ethane, because in the ethane, we only had hydrogen interactions. Now we have a bigger group, the methyl group, playing a role in our energy diagram here. Okay, so, excuse me. Questions about that free rotation and drawing Newman diagrams? Okay, excellent. All right, so now let's go to cycloalkanes, okay? In cycloalkanes, you can't always get that perfect 109.5 degree geometry because you don't have enough carbons to do it. You have too many carbons to do it. You have, it's flopping around, and so you have things kind of interacting with each other. And therefore, cycloalkanes don't actually all have the same relative stability. And we can actually determine this by doing an experiment called the heat of combustion experiment. So by the heat of combustion experiment, it means the more energy it gave off, then the more potential energy it had. Okay, so let's look at that. If we look at the heat of combustion for our butane there, we see that we get out of it 2,877 kilojoules per mole of heat from that reaction. Okay. If we take an isomer of it, where we just move the methyl group on over here, we actually end up getting out 2,837 kilojoules per mole. So less heat is given off, okay? That means it had less potential energy. That means that the isobutane must have been more stable, okay? Because as potential energy rises, you're adding energy to the system, as your potential lowers, it becomes more stable. So the fact that we're giving out less heat during the combustion process means our isobutane must be more stable. Okay, so by just burning things, we can figure out the relative potential energy of each of these compounds. And we can do that for cyclos as well. Okay, when we do that for cyclos, we're going to see the effect of having the strain of having very small rings and maybe the inability to get into a comfortable position in large rings. So the smallest one we can do is this 3 rings, cyclopropane, right here. Can't make a ring out of 2 atoms, so it's got to be cyclopropane. We see that the heat of combustion is pretty high. And if we account for the number of carbon and hydrogens, so we're comparing apples to apples, which would be this, we actually see that that ring makes that compound 115 kilojoules per mole less stable than if it was a hydrocarbon, a straight chain hydrocarbon. And we think about that, we have 3 Sp3 hybridized orbitals that are in 60 degrees from each other, not the 109.5, 60 degrees. That's very, very tight, very, very difficult to do. And that causes this strain on the system, which makes it less stable. Okay. When we have we add just 1 carbon, well, that's great. That takes it out here, but those are 90 degrees apart. Still not 109.5. And so we anticipate there's some ring strain there. And when we do the calculation, we do see that there is ring strain there. We still are taking our 109.5 degree bonds and turning them into a 90 degree box. Okay. Well, let's go up 1 more carbon. We're getting closer to where we think we can make it lay flat. And well, that's true. We get pretty close. It drops significantly. So we're getting really close at 109.5. It's probably closer to 120 to try to make it all flat. And so we see that interaction. By the time we get to 6, it drops to 0. So 6 is the magic number. And so that's why the title of the chapter is actually cyclohexanes and not cycloalkanes. Okay. Now, once you go up to 7, 8, 9, and 10, we start getting ring strain again. Okay. It's not, it can't completely be in that eclipsed formation. Every single bond in that thing cannot be in that completely, staggered configuration. Because it can't be completely staggered, it has ring strain in it, which means that in our configuration of 6 carbons, we must be able to draw Newman projections where every single atom is in that staggered configuration. And we can actually, this is not theoretical, these are directly measured. We know that the cyclohexane is relatively the most stable cyclohexane. So that's why a lot of people actually like to use cyclohexane as an example, because we can see a lot of stuff in it. So in the case of the cyclopropane, our ring strain is so high, and notice that these hydrogens are completely eclipsed with each other. There is no way for them to get out of the way. There is no way for them to be in a staggered configuration. So not only do we have the ring strain from having the bonds be so, the bond angle being so small, we also have it from all the eclipsed hydrogens. So it's a combination of both things. So not being 109 degrees and eclipsed. So we need to find something that we can not see that eclipsed and that ring strain. So we find that in our cyclohexane, okay? And let me show you that right here, and I'll go back to that one. So in cyclohexane, if we draw the most common configuration called the chair configuration, we can look at it in a Newman projection, looking down, let's see which bonds we're looking down. We're looking down 6 and 5. So we're looking down this bond here and this bond here in our Newman projection. And notice what we see. All of our hydrogens and all of our carbons are in their staggered configuration. And we only have a Gauche configuration for the 2 carbons that are bound in the middle. Okay. So everything's staggered. Nothing is eclipsed. Okay. So that means that we have the lowest possible strain we have here, because all the bonds are 109.5 degrees and we have no eclipsed atoms. Okay. That's why this is in its perfectly lowest energy state. That's why it has 0 ring strain and 0 motion. However, because we have rotation, we can't open it up because that would break a bond, but we can have the bonds rotate, but it's constrained by the fact that it has a ring. So we have a bunch of different ways we can do that. For example, if we were to take this and this end right here and push it down to make it flat, we have what we call a half chair. Oh, I'm sorry. This is the chair configuration. It's the most common. And I'll show you how to draw it real easy by the end of the lecture. This is the half chair. And that takes a significant amount of energy because now we're eclipsing all of the hydrogens over here. And we're eclipsing all of the adjacent carbons as well. So that's why that energy barrier is so high. We started to do that at eclipsing. We still are trying to make everything at 109.5 degrees, but the eclipsing is the part that's giving it. Then if we were to have this kind of flip up a little bit, that gives us the twist boat. It's a little better. We only have a few things eclipsed. Then we go up to the boat here, which is where we have a big problem because we start seeing the hydrogens that are on here are going to start impinging on each other. Then it can twist again, go back to the half chair. And by the time it flips all the way over, we have inverted to the other chair, which is the very stable system. Okay, questions on the fact that these are, all we're doing is trying to get rotation around a bond, but it can't flop around too much, so it goes through these different configurations. Okay, now, the next thing I want to talk about is definitions of the different kinds of atoms. So what I want to do is I want to draw an axis through this. Actually, let me do it this way. This is an axis through, that's one, there, through the middle of that bond. So you can imagine there's an axis running through the middle of this. And if we were to draw that cyclohexane flat.
Dr. Irvin.
Yes.
It's 150.
Oh, I'm sorry. Thank you very much. I got excited. Okay, we'll pick up here on Monday, and then we'll take the rest of that day to do the review for the exam. Okay? All right.
Thank you.
And I'm going to stop sharing and stop recording.
Thank you.
Thank you for